Three-phase AC motors. They seem to be everywhere in an industrial operation. They drive air compressors, conveyor belts, pumps, elevators, fans, even generators. Yeah, they drive just about everything in the plant. They're smaller than most industrial equipment, but don't let their size fool you. They're economical and efficient and reliable. They require only a minimum of maintenance, but the three-phase motor is still a machine, and machines break down. When an AC motor in your plant malfunctions, it's your job to fix it. Let's take a look at a typical three-phase AC motor. There are two basic parts to any motor: the stator and the rotor. Inside the stator's frame is an iron core which is formed in the shape of a ring. The core is slotted, and conducting coils or windings are set into these slots. These are the motor leads. They make the electrical connection between the motor and its power supply. Inside the motor, they're connected to the stator coils or windings. Alternating current flows from the leads into the stator windings, and a magnetic field is produced in the stator. This magnetic field rotates. This is the rotor. It's positioned on a shaft. When the magnetic field of the stator rotates, the rotor and shaft turn with it, and mechanical power is produced. Sounds simple, doesn't it? But as an electrician, you have to understand how this happens in three-phase motors. You'll be responsible not only for maintaining these motors, but for detecting malfunctions in their various parts. Now, a simple understanding just isn't enough. So let's take a closer look at what happens to make a motor run. We'll begin by reviewing some basic principles of alternating current. Then we'll see what occurs in the stator of a motor when three-phase AC current flows through it. You may already know that alternating current flows through a conductor in one direction, reverses, and then flows in the opposite direction. Well, the amount of current flowing continuously changes too. The current increases to its maximum value and then decreases. Then the current reverses its direction once again. It increases to its maximum value and then decreases, but in the opposite direction. Now, this can be better understood by looking at a sine curve that shows how AC current changes. The sine curve for a single-phase alternating current is fairly simple to understand. The curve represents the intensity of the current flow. Starting when the current is 0, it increases to its maximum, then decreases. The direction of the current changes, and the current again increases to maximum and then decreases. Each repetition is called one cycle, and there are usually 60 cycles of alternating current in every second. Now, that's how AC current changes. Now, let's briefly review how an AC current creates an electromagnetic field. When current flows through a conductor, it produces a magnetic field. If we could look into the end of a wire with current flowing through it, we'd see what the magnetic field looks like. As the current increases, the magnetic field expands outward. It becomes stronger. Then the current begins to decrease, and so does its magnetic field. The current reverses then, begins to increase again, and so does its magnetic field. After both have reached maximum, the current and its magnetic field decrease until the current is again 0. One full cycle of alternating current is completed. The magnetic field of a conductor is intensified by forming the conductor into a coil. The more turns in the coil, the greater the strength of the magnetic field. Now, this magnetic field exhibits polarity, or in simpler terms, has a north and a south pole. The position of the magnetic poles depends on the way the coil is wound. Now, when the current changes direction, the polarity of the magnetic field reverses. The north pole is where the south pole has been, and the south pole is where the north pole has been. For example, during the first half of a cycle, the magnetic field in this coil has a north pole and a south pole. the strength of the magnetic field increases and decreases along with the current. When the current reverses direction, the magnetic field reverses. Once again, the magnetic field increases and decreases with the current. But what would happen if we had two coils in series? Most AC motors have at least two coils in series, so let's look at what happens when there are two coils. As current flows through the two coils, they each produce their own magnetic field, and each has a north and south pole. We're going to concentrate on the area between the two coils. During the first half of a cycle, the magnetic field between the coils increases in strength. There is a north pole and a south pole. After reaching maximum strength, the fields collapse back into the coils. During the second half of a cycle, the magnetic field reverses. The south pole is at the top and the north pole at the bottom. Once again, the magnetic field increases from 0 to maximum strength, then decreases to 0. This is repeated for each cycle of alternating current. Now that you know what happens in a single phase, let's talk about three-phase alternating current. Now remember, each phase is actually a separate current and flows through a separate conductor. The currents are similar, but they're produced at intervals. In other words, they are out of phase. By viewing the sine curves of the three currents, their relationship can be clarified. Now, try to imagine what occurs when the three-phase current is first generated. We'll simplify the process here to make it easier to understand. In actual fact, all three currents are generated at once, but we're going to look at them as if they were generated one at a time, so you can see the relationship between them. And when the current is first generated, a single current is transmitted through a conductor. This is the first phase current. A third of the way into the first current cycle, another current is produced and travels through a second conductor. The two currents are the same, only their starting times are different. Two-thirds into the first current cycle, a third current is generated, and this current is also transmitted through a separate conductor. When the three sine curves are plotted on the same axis, you can see the relationship between the three currents as they act simultaneously. This simultaneous relationship is found in the stator windings of three-phase motors. In a three-phase motor, there's one lead or wire for each of the three-phase currents. Each lead is connected to coils in the stator of the motor. In addition, the coils are usually linked together through a common point. A motor whose stator coils are connected in this way through a common point is said to be Y or star connected. It is so called because the schematic is Y or star shaped. Inside the stator are the stator coils, or pole phases as they're sometimes called. There are 2 stator coils for each phase, for a total of 6 coils in the stator of the motor. The coils are connected together in pairs. The first coil pair looks like this. 120 degrees from the first coil pair is the second coil pair. 120 degrees from the second coil pair is the third pair. But what happens when a three-phase alternating current flows through these stator windings? A magnetic field is produced in the stator. Let's take a look at how this magnetic field is generated and how it rotates in the stator of the motor. We're going to slow the rotation so you can see what it looks like. We'll use colors to represent the magnetic field. Green is north and yellow south. And when the first coil pair is energized, current flows through it. This current produces a magnetic field between the coils. The magnetic field changes with the current, and the north and south poles of the coils reverse with the change in current direction. The second phase current flows through the second coil pair, but the first phase is further along in its current cycle, so the magnetic field generated by each coil pair differs in intensity. Now, watch what happens when the third coil pair is energized. Because the third phase current is generated 2/3 of the way into the first phase cycle, the magnetic field generated by each coil pair differs in intensity. The magnetic field between the stator coils, therefore, rotates. The speed at which the magnetic field rotates depends on the frequency of the current. When the frequency of the current is 60 hertz, the magnetic field produced in this type of motor rotates 60 full turns in 1 second. That's quite a bit faster than what you're actually seeing here. The stator we've been looking at is a 2-pole stator. The magnetic field has 2 poles per phase. However, not all AC motors have 6 coils and only 2 poles per phase. Some 3-phase stators have 4 or more poles. In a 4-pole stator, there are 12 coils, 4 poles for each phase. The magnetic field of a 4-pole stator turns half as fast as the magnetic field of a 2-pole stator. The greater the number of poles in the stator, the slower the rotation of the magnetic field. This is important because the speed of the stator field affects the speed at which the rotor of the motor turns. Well, I'm going to pause for a few moments here so that you can check your understanding of the things we've already covered. Before proceeding, please review the first section of your text. Take the necessary time to ensure that you have a firm understanding of 3-phase currents and their corresponding sine waves. Be sure you understand the way a rotating magnetic field is produced by these 3-phase currents. In the first section of this tape, we showed that a 3-phase alternating current in the stator windings of a motor produces a rotating magnetic field. Now, this rotating stator field acts upon the rotor and makes it turn. Now let's look at the rotor. There are 2 kinds of 3-phase induction motors, the squirrel-cage type and the wound rotor type. The stators in both these types of motors are basically the same. It is their rotors that are built differently. And that's how you tell which kind of a motor it is, by its rotor. We'll start with a squirrel-cage rotor. The squirrel-cage rotor is made of conducting bars. Now, these bars are shorted together by end rings that are also made of a conducting material. The rotor bars, together with their end rings, are attached to a shaft, and the whole assembly turns together. Now let's see why the rotor turns. Whenever there is relative movement between a conductor and a magnetic field, there's a voltage induced in the conductor. The rotor, you remember, has conducting bars. Relative movement between the stator's field and the rotor bars induces a voltage. Because the magnetic field of the stator is rotating, the voltage induced into the rotor creates a flow of alternating current in the rotor bars. As the stator's magnetic field continues to rotate, the current produces a magnetic field in the rotor which expands and collapses. And this pulsating field interacts with the stator's rotating field, causing the rotor to turn in the same direction. The pulsation of the rotor's magnetic field causes relative motion between it and the stator coils. The stator coils are conductors, so once again there's relative motion between a conductor and a magnetic field. Because of this relative motion, voltage is induced in the stator by the rotor. This voltage increases the effective voltage in the stator. Well, there are actually 3 voltages that combine to produce the effective voltage in the stator. One is the applied voltage that comes from a power source. The second comes from the inductance of the stator. It opposes the applied voltage. The third voltage is induced into the stator by the rotor. It aids the applied voltage. The 3 voltages combine to produce one effective voltage. Now, this effective voltage is greatest when the motor is first started. At motor start, The stator's magnetic field is rotating at high speed, but the rotor is just beginning to turn. The difference between the speed of the rotor and the speed of the stator's field is maximum, and the voltage induced in the stator is also maximum. Therefore, current flow is very high at motor start. In fact, in a typical AC motor, starting current is 3 to 5 times higher than the normal running current of the motor. If an ammeter is connected to the motor, we can see this increase in current when the motor is first started. As the speed of the rotor increases, the difference between its speed and the speed of the magnetic field gets smaller. This causes less voltage to be induced into the stator. Motor current then decreases. If the rotor's speed were to increase to the exact speed of the stator's field, no current would be induced into the rotor, and the rotor's magnetic field would be 0. But in reality, there's always some resistance to rotor rotation. Now, this resistance is usually from friction within the motor, the load the motor is driving, or both. The resistance causes the rotor to turn more slowly so that it never reaches the exact speed of the stator's rotating magnetic field. Because of this, there's always some relative motion between the rotor and the magnetic field of the stator. Although the rotor's speed is always a little slower than the stator field, their speeds are related. And if the speed of the stator's magnetic field is cut in half, the rotor slows by approximately half also. The difference between the speed of the stator's magnetic field and the speed of the rotor is called slip. And slip is very important because it determines the amount of power the motor produces. It also affects the amount of voltage induced in the stator. The greater the slip, the greater the effective voltage in the stator. So, when the rotor's speed decreases, its slip increases. And so does the voltage induced in the stator. This means the current in the stator goes up. Now, if we place load on a motor, the rotor's resistance to rotation increases. In other words, the rotor slows down. Because of this slowing down, there is more relative motion between the stator field and the rotor, so slip increases. More voltage is then induced in the rotor bars. More voltage means more current flows, and the magnetic field of the rotor gets stronger. The rotor now turns more strongly, and the motor produces more power. At the same time, there's an increase in the amount of voltage induced in the stator. This increase in voltage causes current flow to go up, and the electrical power that the motor is using also increases. Up until now, we've been talking about what makes a squirrel-cage rotor turn. But what we've said also applies to a wound rotor. A wound rotor has coils that are made of wire. The next thing we're going to look at is a wound rotor. Wound rotors are more expensive to make than squirrel-cage rotors, so they are not commonly used, but because it's possible to control the speed of wound rotor motors, they are sometimes used where speed control is necessary. A wound rotor motor operates exactly like a squirrel-cage motor we've just seen, with one exception. To gain speed control, slip rings and brushes are used to make the connection between external resistances and the rotor coils. And this puts the external resistances in series with the rotor windings. A typical wound rotor circuit is shown here in a schematic representation. These symbols represent the rotor coils. The rotor is wound to match the stator. As in the stator, the wound rotor has separate coils for each of the 3 phases. Current that's induced into the rotor coils passes through the slip rings and brushes to get out of the motor. Most wound rotor motors have several sets of resistors in their rotor circuits, which are used to run the motor at different speeds. The motor runs slowest when all of the resistors are in the circuit. If a current path is provided to bypass one set of resistors, the motor runs faster. If an additional set of resistors is bypassed, it runs even faster. And if all the resistors are bypassed, the motor runs at maximum speed. Well, you've seen how the rotating magnetic field of the stator causes the rotor to turn. You should understand that rotor speed is determined by the speed of this rotating stator field. The difference between the speed of the rotor and the speed of the stator's magnetic field is known as slip. We've discussed how a change in slip affects how strongly the rotor turns. We've looked at two common types of rotors, the squirrel cage and the wound rotor. You know that the squirrel cage is the most common type of motor and that the wound rotor motors are used when speed control is needed. Well, you should have a basic understanding of how the speed of a wound rotor motor is controlled. It's a lot of information to cover. So take the time now to review this material in your text. Go over it several times if you need to, until you have a good understanding of the subject. Oftentimes, you'll be asked to inspect motors that seem to be operating normally. Your job will be to detect any problems before they become critical. This is called preventive maintenance. When you take good care of motors, many major problems can be avoided. So it's an important part of your job to carefully maintain the motors in your plant to ensure their continued performance. And we're going to show you how to do just that. First, we'll show you how to inspect a motor that's operating. Then we'll show you how to inspect a motor that's not running. By treating electricity with respect and with caution, you'll be able to work with it quite safely. But remember, it can be dangerous. So before inspecting a motor that's operating, take the necessary safety precautions. Remove any wristwatches, rings, or other accessories that might conduct electricity. Loose clothing and unbuttoned shirt cuffs present another hazard. They can become entangled in moving machinery and endanger your life. Always keep in mind the safety of yourself and others. After taking all the precautions you can to ensure safety, you can begin to examine the motor. Try to use all your senses to their best advantage. Visually inspect the motor for any loose or broken parts. Check the air vents for dirt or grease or other obstructions to the motor's ventilation. If a blockage is found, the motor must be shut down and the blockage removed. As well as looking, listen. The motor should give a smooth, steady sound. An unsteady sound or an increase in motor noise is an indication of trouble. Vibration can cause an unusual noise in the motor, so touch the motor. The vibration can be felt as well as heard. By touching it, you may be able to find the greatest area of vibration and thereby locate the problem. But please be extremely careful when touching near the bearings of the motor. If the problem is in this area, excessive heat will be generated there, enough to burn you. You should also look for unusual movement of the shaft or vibration of the motor. Some motors have instruments to measure temperature and vibration permanently installed in them. You can easily take a reading for these motors. For other motors, though, you'll have to use a vibration meter to measure the vibration of the motor. And a contact pyrometer to measure its temperature. In either case, readings should be compared with previous readings taken under the same conditions to see if a trend is developing. If the motor you're inspecting is a wound rotor motor, pay special attention to the brushes and brush riggings. Replace any brushes that are worn. Make sure all the brushes touch their slip rings and clean the slip rings with a canvas wiper. At the motor control center, the electrical current which flows to the motor can be checked for a balance of phases. By unbolting the front of the control center's enclosure, the controls are revealed. These three conductors supply the motor's power. So we use a clamp-on ammeter to check the current flow in them. In other cases, permanently installed ammeters may be used. The current in each of the phases should be the same. If they're not, tell your supervisor. A phase imbalance can be caused by a variety of problems, such as grounds, opens, shorts, or mechanical misalignment. Now, let's take a look at how to inspect a motor that's not operating. For many motors, particularly ones that are located outside in the weather, a heater is used to keep them dry during shutdown. So, one of the first things to check on a stopped motor is whether its heater or heaters are working. Make sure you follow all safety precautions when you're working around these heaters. To ensure a motor won't be started while you're inspecting it, tag the motor out or have it tagged out according to your plant's procedures. Then, begin your inspection by, once again, using your sight. Through the ventilation slots at the end of the motor, you can usually see the stator windings. Look for discoloration of the motor's insulation, signs of burnt insulation, and dirt. Moisture can be a major problem for a motor, so whenever possible, check for dampness in and around the motor. Remember to check the bearing housing for signs of leaking grease or oil. On a wound rotor motor, examine the brushes, brush rigging, and slip rings. Be sure you notice the surface of those slip rings. If they're grooved or discolored, report their condition to your supervisor. In order to operate correctly, the rotor must be centered in the stator of the motor. Once in a while, you may be asked to check the spacing between the rotor and the stator to see if it's centered. On some motors, you can do this without taking the motor apart. On this motor, there are 4 slots at each end of the stator. Take a reading at each one of them by inserting feeler gauges. The feeler gauges go through the slot and in between the rotor and the stator. The readings should be the same at each location. If they're not, you should report it. The most common preventive maintenance test for a 3-phase motor is the insulation test. For this, a high-range ohm meter known as a megohm meter is used. First, make sure the motor is tagged out according to plant procedures. It's always a good idea to verify that the motor is really de-energized and that there's no residual charge on the motor. Then, it's disconnected at the motor starter or at the connection point at the motor. In this case, we've disconnected these 3 leads in the motor starter. This isolates it from its power source. Then, the motor leads are clipped together. Before going any further with the test connections, the megohm meter and its ground connection should be tested. The megohm meter is tested first by operating it to see if it will indicate infinite resistance. Then the leads are connected together to see if the meter will indicate 0 resistance. Next, the ground lead of the megohm meter is attached to the ground on the cabinet. The ground connection is tested by connecting the red lead to ground at another location. With the lead set up like that, the meter should indicate 0 resistance. Then, the megohm meter's line lead is connected to the motor leads. The megohm meter is operated for 1 minute and a reading is taken. The reading we get here is nearly infinity. As a rule of thumb, you should get a reading of at least 1 megohm for each 1,000 rated volts, with a minimum of 1 megohm. And if you don't, you've got a problem. The motor has at least a partial ground. We'll discuss what to do about that a little later. Even if the reading is acceptable, it should be compared to previous readings to see if a trend is developing. In this way, deteriorating insulation can be detected before it fails. Because it receives a charge from the megohm meter, the motor must be discharged at the end of the test. You discharge it for approximately 4 times the length of the insulation test. Once you've discharged it, reconnect the leads, remove the tags, and return it to service. Preventive maintenance is a very important part of your job as an electrician. So take the time now to really learn how to take care of your motors. When you're on the job, you'll find out that it was worth it. Although preventive maintenance is important to keep motors running, it can't guarantee trouble-free operation. When a three-phase motor breaks down, it's your job to find out why. The best way to do this is to eliminate any of the possible causes of a motor problem. Often the problem won't be in the motor itself, but in the equipment the motor is driving or in the motor controllers. So do yourself a favor and check there first. You save yourself a lot of time and bother if you do. Well, let's say you've checked to see if the problem was caused by a mechanical failure, and it wasn't. And then you check the power supply and the control system, and still no sign of trouble. Well, there's only one place left: the motor. The first step in testing a motor will always be to see that it is tagged out according to your plant's procedures. When you prepare to test a motor, try to use all your senses. That includes common sense. Say you smell burnt insulation and the motor's a squirrel-cage motor. Well, the rotor in a squirrel-cage motor doesn't have any insulation, so the problem's got to be in the stator. But suppose you smell burnt insulation in a wound rotor motor. There's insulation in the stator and the rotor in that kind of motor, so where do you look first? Well, if you look in the windings of the rotor, you might be able to see the burnt insulation. If you do see burnt insulation, you're going to have to test the rotor. Let's say you've looked at the motor over carefully, but you didn't find any sign of the trouble. You know there's something wrong with the motor because it isn't operating right. Maybe it won't run at all. Well, you know that you're going to have to test to find out what's wrong with it. But where's the best place to start? Well, most problems in three-phase motors occur in the stators, so that's the best place to begin your testing. There are three common types of faults to look for in the stator of a motor: grounds, opens, and shorts. When there's a ground in the stator, there's low resistance through the insulation between the stator's coils and the motor frame. You've seen how to test for grounds in the stator. It's done with a Ohm Meter. Well, if the ground is present, the Ohm Meter reading is lower than normal. It may even be zero. But you still need to know what's causing the ground to fix it. So look for any signs of moisture. Moisture is a common cause of grounds. If you do notice moisture, you may be able to solve the problem by drying the motor. This might be done by using heat lamps or by blowing hot air through the motor. But there are lots of ways of drying a motor. Now, if there's any question in your mind, ask your supervisor what procedure is used in your plant. Check to see if there's any chafing of the leads on the stator coils. If the ground's caused by chafing of the leads, you probably can re-insulate them, and that'll take care of the problem. If the ground is inside the motor and drying it doesn't help, the motor must be disassembled to find the problem. Now, when you've looked a motor over and you still can't seem to find a reason for a ground, then go to your supervisor. He'll decide what to do from there. Suppose the Ohm Meter reading doesn't indicate a ground. Well, the next thing to test for is an open. When there's a break in a stator coil, the current no longer has a complete path. This is called an open. There are a couple of ways to test for opens. Which way you test for one depends on how the motor is connected inside, whether it is a Y or delta connection. In a Y-connected motor, the stator coils are connected together through a common point. And in a delta-connected motor, the stator coils are linked end to end. You can't tell how the motor is connected by looking at its leads. You can, however, check the nameplate of the motor. Usually, the information you need is located there. If it isn't, try to find it in the manufacturer's manual. Most three-phase motors are Y-connected, but regardless of the type of coil connection in the stator, a multimeter is used to test for an open. The multimeter is set for resistance, and each current path is tested. Let's look at the schematic of a Y-connected motor with an open in one coil. If we were to take a reading between lead 1 and lead 2, the open in coil 1 would prevent current from flowing. The multimeter would show infinite resistance. Likewise, if we were to take a reading between lead 1 and lead 3, the open in coil 1 would prevent continuity from being indicated on our multimeter. But if we measured current flow between lead 2 and lead 3, we would get a reading. An open doesn't exist in the current path between those two leads, so current can flow between these 2 points. Now let's look at an example of this test. The 3 leads are marked according to their phases. Red tape is used to indicate the first phase lead, white for the second phase lead, and blue for the third phase lead. The multimeter is set for resistance, and it is connected to lead 1, which is marked with red tape, and lead 2, which is marked with white tape. The multimeter shows infinite resistance between these 2 leads. Next, a reading is taken between lead 1 and lead 3. There is again infinite resistance between lead 1 and lead 3. At this point in our test, we might assume that the open is in coil 1. We know that the break in the current path is between lead 1 and lead 2, or between lead 1 and lead 3. And it's pretty certain that the open is in coil 1, but we want to make absolutely sure. So we take a reading between lead 2 and lead 3. The multimeter reads normal resistance. Now we know for sure that the open can't be in coil 2 or coil 3. If there were an open in either one of the coils, this current path would not have normal resistance. Since it did, we know the open is in coil 1. Don't ever assume that you know exactly where an open is until you check every one of the current paths. In a delta wound motor, you always get continuity between 2 leads, even if there's an open in one of the coils. This is because of the delta connection. Let's look at the schematic of a delta wound motor. We'll say there's an open in one coil. Normally, the reading for each current path should be almost the same, but this isn't the case here. Because of the open, the current can't follow its regular path, so it finds another. The open prevents the current from flowing directly between lead 1 and 2. Instead, the current flows through the other coils. When we take our reading, we find the resistance is high in comparison to the other 2 current paths. In fact, it's almost double the other 2 readings. That's because the current has to flow through 2 pairs of coils instead of just 1. Now let's test a delta wound motor. Connect the multimeter to lead 1 and lead 2 and take a reading. Then write the reading down for later reference. Next, take a reading for lead 1 and lead 3. Again, write down the reading. You already can notice a big difference in the readings. The reading is a lot greater between lead 1 and lead 2 than between leads 1 and 3. You suspect that the open is in coil 1 or 2, but you don't know which one. So test between leads 3 and 2. The reading is about the same as for lead 1 and 3. It's also about half the reading for 1 and 2. Therefore, the open is in coil 1. Suppose you check the nameplate of the motor and it didn't show what kind of connection the motor has, and you can't seem to find the manufacturer's manual. Well, there's really no problem. Just test it as if it were delta connected. That way, you look for balanced resistances rather than just continuity. By looking for a balance of resistances, you'll find out if there's an open, regardless of which kind of motor it is. Okay, say you test the stator for grounds. There aren't any. Then you test for opens, no opens. Well, the problem is most likely a short. A short is an accidental current path of low resistance. When a short occurs, a conducting path interferes with one of the normal current paths. The current takes the path of least resistance through this new course. Now, you can try to locate the short by testing for resistance balance in the current paths, but chances are you won't be able to find it because the imbalance may be so small that you won't see it on your meter. But if you're sure there's a problem in the stator and you've eliminated ground and opens, you can usually assume that the problem is a short. Then, in most cases, the motor has to be sent out to be rewound. Now, take the time to carefully review this material in your text. Make certain you understand what's been said about grounds, opens, and shorts in the stator of a three-phase AC motor. You've checked the stator of a motor for grounds and opens and shorts, and now it's time to test the rotor. The problems to look for in a rotor are the same as those in a stator: grounds, opens, and shorts. We'll begin by looking at a wound rotor. Now, this is the same schematic that we looked at earlier. It shows the rotor circuit for a wound rotor motor. Remember that the rotor circuit contains both the rotor coils and external resistances, and that they are connected together by means of slip rings and brushes. Let's first test for grounds. As you did in the stator, you use a Ohm meter to test for grounds in the rotor circuit. The ground could be in the rotor itself or in the external resistances. We'll begin by testing the rotor. We'll remove the brush rigging from this particular wound rotor so that you can more clearly see this test. Take the Ohm meter and attach its ground lead to the rotor shaft. Hold the line lead against one of the slip rings. The coils of this wound rotor are connected together through a common point, so the line lead need only touch one of the slip rings to test all of the coils. Be very careful not to touch the slip rings or the uninsulated portion of the lead with your hands. The Ohm meter could give you a severe shock. If a ground is present in any of the coils, the meter registers less than normal, or perhaps even zero. Once you know there's a ground in the rotor, you might try drying it out, and if that doesn't work, the rotor will have to be removed and repaired. Well, next we'll test the external resistances. Attach the ground lead to ground near the external resistances, and attach the line lead to one of the brushes. Now you can test the resistor circuit separately. Make sure you test the rotor and external resistances separately and double check them for accuracy. The meter in this case reads infinity. This means that a ground does not exist in the circuit. But if you did find a ground, you could locate it by following the wiring or by separation of the circuit into smaller parts and testing each part until the ground is located. Now, after checking for grounds, the next step is to test for opens. You use a multimeter for this test, and remember, you still need to test the rotor and the external resistances separately. Test the slip rings 2 at a time. to measure the resistance through the coils. This is similar to testing for opens in the stator. Test the first and second slip rings. The first and third. And then the second and third slip rings. The multimeter in this test reads 14 ohms for each reading taken. And remember, you're looking for a balance of resistances. If you see an imbalance in the readings, there's probably an open in the circuit. Now, test the external resistances for opens. Test the top of the brushes 2 at a time. The normal resistance will usually be indicated in the equipment manual or drawings. All 3 readings should be equal to each other. If you see an imbalance in the readings, there's probably an open in the external resistances. Be careful when you check your readings in either of these tests. If you see there's a very low one, there may be a short in the circuit you're testing. To detect a short, first eliminate grounds and opens as possible causes of the motor's trouble. If there's no indication that a ground or an open exists in any part of the circuit, then suspect a short. If you suspect a short in the rotor coils, remove the rotor and visually examine it. Look for burn marks, which are a sign that a short has occurred. If you can't see any visual signs, set the rotor in a growler and place a hacksaw blade alongside it. If there's a short, the blade will vibrate. Don't bother looking for shorts in a squirrel-cage rotor. The rotor bars are already shorted together intentionally by end rings. The squirrel-cage conducting bars aren't insulated from the rotor either, so grounds aren't a problem in a squirrel-cage rotor. But opens can occur. When a rotor bar separates from its end ring, an open occurs in the current path. A visual inspection of the rotor bars and its end rings is all that is needed to verify an open in a squirrel cage motor. Well, you've seen how to test for grounds, opens, and shorts in the wound rotor of a 3-phase motor. You now know that grounds and shorts aren't a problem in squirrel cage rotors because of their construction. You know that a visual inspection of a squirrel cage rotor's bars and end rings will tell you if an open exists in the rotor. Now, take the time to review this information and make sure that you've mastered it. Sometimes you'll find it necessary to disassemble a motor. Some plants that have a problem with dust take their motors apart on a regular basis to blow the dust out of them. As a part of troubleshooting, whether it's in the stator of the motor or the rotor, you might have to take the motor apart. Well, the first step is to tag the motor out according to your plant's procedures. Now remember, don't touch the power leads until the power supply has been tagged out and the leads have been grounded. Then the power leads must be disconnected from the power source. Remove the cover to the power leads. After unwrapping the insulation tape which surrounds the leads, unbolt the leads. Each lead should be marked after it's unbolted. Oftentimes, colored tape is used to mark each lead. Whatever the method your plant uses for marking, make absolutely sure that you mark the leads correctly. If any 2 of the leads are reversed during reassembly, the motor will turn in the wrong direction. Keep in mind that you won't always be the one to put those leads back. Another electrician may be assigned the reassembly task, so the marking must be clear enough for someone else to understand. After the power leads have been marked and disconnected, the motor is disconnected from the equipment it drives. Usually this is accomplished by taking apart a coupling. Once the motor is disconnected electrically and mechanically, it can be removed from its foundation and taken to the shop. But many times, especially with large motors, the work is done without removing the motor from its foundation. If you're working on a motor that is on its foundation, you needn't disconnect the power leads, but be sure the power supply is tagged out and that the motor leads are grounded to drain off any residual charge. Now, if the motor you're working on is a wound rotor motor, you would first remove the brushes and brush rigging. Other than that, the disassembly of either a wound rotor or a squirrel cage motor is pretty much the same. We'll see a squirrel cage motor taken apart. Prepare the work area where you intend to place the rotor after it is removed by laying a cloth down or placing V-blocks on the bench. Next, the end bells are marked. The end bells are metal pieces that cover the ends of the motor frame and support the bearings. Marks are made on each end bell so that they can be replaced on the correct end of the motor when it's time to reassemble the motor. Then, the bearing retainers must be unscrewed. The bearing retainers hold the bearings that support the rotor in the end bells. Once the bearing retainers have been unscrewed, the end bells can be unbolted and removed from both ends. Now, the rotor can be lifted out of the motor. The rotor may be too heavy for you to lift by yourself, so don't hesitate to ask someone to help you. Lift the rotor from the motor and lay it on the V-blocks or cloth. Don't drag the rotor across the stator poles. Dragging it could damage it and the stator. The motor is now disassembled and ready for inspection. Begin by carefully looking over the rotor. As with any visual inspection, look for anything out of the ordinary. Inspect the rotor for burn marks where high current flows may have caused excessive heating. A squirrel cage rotor should be carefully examined for opens between the end rings and the rotor bars. Look for bent bars and other damaged or broken parts. If the rotor is a wound rotor, carefully examine the windings. Look for burns that could be evidence of grounds, opens, or shorts. Pay particular attention to the winding insulation. If you have a question on the rotor's condition, ask someone with more experience to take a look. Then check the bearings. This motor has ball bearings, so we rotate them to make sure they turn easily and smoothly. If they don't, they must be replaced. Finally, inspect the stator for burn spots, the condition of its insulation, and loose or damaged parts. Carefully examine the entire stator, not just its ends. When your inspection is finished, take the time to clean the motor. Use cloths to cover the bearings. Don't forget to wear a mask, gloves, and eye protection when cleaning a motor. Use compressed air to blow the rotor free of dust. Do the same for the stator. And make sure you rid it of as much dust as possible. Next, spray the rotor with solvent to clean it further. Make sure you use an approved solvent. If you don't, you could seriously damage the motor. After spraying the rotor, spray the stator. Then allow the motor to dry completely before you begin to reassemble it. Putting the motor back together is easy. Lift the rotor into position, being careful not to let it drag on the stator poles. Then check the markings on the end bells and make sure you replace them on the right end and in the position indicated by their markings. Align the end bell mark with the mark on the frame. If you don't, misalignment and binding can result. As the end bell is moved into position, it'll be necessary to raise the rotor slightly. This is to allow the rotor bearings to slide easily into the end bell. After replacing the end bells, put the bearing retainer screws back in and make sure the shaft is free to turn. The motor is now back together, but you need to do some electrical tests before reconnecting the power leads. The motor should be tested for grounds with a Ohm Meter and checked for balanced resistances with a Multimeter. Next, reconnect the power leads. Check the lead markings and reconnect them in their proper order. Then wrap the leads with insulation tape. Insulation tape prevents grounds from occurring and also protects the leads. Now, test the motor by turning it on briefly. This is called jogging the motor. By doing this, you'll be able to see if the motor is turning in the right direction and that it is indeed operating correctly. Reconnect the motor to the mechanical equipment it drives, and the motor is ready to operate again. Finally, check the current flow to the motor while it's operating. Then it's ready to be returned to service. As an electrician, you'll be working with a lot of three-phase AC motors. Not all of them will look like the one we've just shown you, but the steps in disassembling and reassembling any three-phase motor are basically the same. Now, we've covered quite a bit of information in this unit, and all of it is important for you to know. Preventive maintenance, motor inspection, motor testing, disassembling and reassembling the three-phase motor. You'll need to know it all to do your job and do it well. So now make sure that you completely understand this material.